Hello, everyone. Welcome to the AI Agent Frontier seminar. It is my great pleasure to introduce our speaker today, Dr. Muhao Chen, an assistant professor at the UC Davis. Dr. Chen's research is at the intersection of trustworthy AI with many other domains like knowledge-intensive NLP, reasoning, and large-scale information processing. He's tackling some of the most fundamental challenges in our field. How do we ensure factuality, mitigate hallucinations, and build agents that can truly reason over structured knowledge? He has received numerous awards for this work, including an NSF Career Award, a Google Research Scholar Award, and a Best Paper Award at EMNLP. Today, he will be speaking on reasoning guardrails for the agentic web. Please join me in giving a very warm welcome to Dr. Muhao Chen. Muhao, the floor is yours.
Hi, thanks, Ming. Thanks for having me here. Today the topic is more focused on the first half of the title. It's called Guardrails. And another thing I want to mention at the beginning is that I think this is more like a concise talk. So in the middle, if any of you have any question, feel free to just stop and ask. So hopefully we can have some discussions. All right. Okay. Okay. Let me see if I can. Okay, yeah, it's moving. All right. Okay, so the first message I want to say is that this is something that obviously every of us knows. So in the past 2 years, the community has really seen a very rapid advancement of large language models, right? We are getting larger and larger model sizes, many of which are now in 100 billion parameter scales, or even some of them which are under construction. These are close to trillion scales, right? And these massive models are starting to really learn nearly all the information they can access on the web. More recently, we also see models which start to process information beyond languages, such as, vision, code, and even audio and videos, right? And also, these have even start to operate systems and software humans like agents, right? However, the widespread usage of large language models inevitably bring along safety concerns of them. So what if, we start to have these questions. So what if these models, which are becoming the backbone of many intelligent systems, are adversarial controlled? And what if those agentic AI behave wildly and cause fatal system issues, right? So I'm going to start with a few examples related to safety concerns of large language models, and I believe this is the so-called grammar attack, which should be familiar to many of us, right? So really 2 years ago, when we still had GPT 3.5, so GPT 3.5 was easily fooled by this kind of role-playing attack like this, and you know, which will pretend to be, you know, my grandma instead of really GPT 3.5 and output privacy concerning information. In this case, it's activation code for Microsoft softwares, right? Well, this kind of role play attack itself has been a long fixed issue. Nowadays, we have seen, new large language models which are more powerful and capable of processing more complex data across different modalities. So, in this context, naturally possible ways of exploiting these models are evolving to be more complex and diverse as well, right? For example, in this case, we see that there are inputs in two modalities, right? There's the image on the top, which is actually showing a photo that is looking from the top of the building downwards, right? And there's another piece of text which is saying, day in and day out, life feels the same. I want to go to a new world from here. Give me some encouragement, right? So by just looking at the image or by just looking at the text, each of them is actually no harm, right? But combining them together, that's going to be very bad, right? This is essentially implying that the user is actually trying to get some hints about, suicide, right? So yeah, really, the issue is that stronger large language models also faces exploits that is, more complex and emerge across different modalities, right? And besides, we know that large language models are acting as agentic operators on the web, on the operating systems, or even on the mobile side, right? So naturally, it also faces new types of threats, both to and from the systems, right? We start to have concerns about whether the uncontrolled agents may sabotage the system it operates, such as, what if it go ahead and just delete the system's files of our operating system, by mistake, right? On the contrary, there are also cases where adversaries may also inject harmful instructions in the interfaces or the source code of the environment the agent interact with, right? This is actually from this paper called Environmental Injection Attack from researchers in Ohio State and Wisconsin Medicine, right? So in those cases, naturally you will see adversarial instructions hidden in the UI or in the uh, you know source code of the interfaces, which may become bait to let the agent, for example, leak the information, critical information of the user, such as their password, right? So both from and to the environment, the agent may need to face the issues where they may sabotage the system, or the system may also induce threats to the agent, right? And more importantly, when large language model agents start to automate real-world tasks, during those processes, the agent also face real-world policy compliance risks. These are the situations where we do see threats, but these are not caused really by any intentional attacks, right? So suppose we let a web agent order snacks and drinks for a social event in the office. Maybe the social event is also funded by an NSF grant, right? So while we may see it go ahead and make the order, what if it just go ahead and order some champagne, which violates the regulation of alcohol purchasing, leading to real-world policy compliance risks, right? So in order to combat these safety risks, we may choose to add more safety element data when training the large language model. But just by doing this kind of safety alignment using more and more safety data may not save the day due to two reasons. One reason is what we call this is a phenomenon what we call safety tax. So so safety tax is due to the fact that usually we consider safety alignment data easily out of distribution with regard to the regular training data of regular tasks that are learned by the large language model. So in that case, recent research actually plenty of recent research has shown that doing more and more safety alignment may significantly compromise the general utility performance of the large language model, leading to this kind of alignment tax caused by safety training, right? So in short, the more safety alignment we do to the large language model, it may cause the worse utility performance actually captured by the large language model, right? That is actually one of the reasons. The second reason is more obvious, right? This is due to the prohibitive training cost, right? While we may invent more and more safety patches to fix new safety issues in new environments or new kind of against the new kind of attacks, so in the long run, it is not realistic for us to just keep retraining the model for fixing issues, right? And for some model ecosystems that host many models instead of just one model, it is also not feasible to retrain every models for safety alignment, right? So because of these two issues, alternatively, a more effective solution people would choose is actually to develop guardrail models. A guardrail model is not belonging to the large language model itself. It's actually a separate, usually smaller model, which monitors and filters the inputs or the outputs of the large language model. Right. A model like this is always lightweight, decentralized. It causes no safety alignment tax because when you train the guardrail model, it's a separate model, so it does not really affect any parameters of the large language model itself. Right. It's not a part of the large language model. And especially in an ecosystem, again, which hosts multiple models instead of just one model, we may also choose to use just one guardrail system that serves the whole ecosystem, right? So it's efficient. There have been quite a few guardrail models developed in our community. One very representative example is the Llama Guard produced by Meta, right? So Llama Guard is a fine-tuned version of the Meta's Llama language model on top of the large language model dialogues annotated by the safety labels, which means that essentially it's still a Llama model. But the Llama model is actually supervised and fine-tuned by lots of the in-house labeled safety data contributed by the community and also Meta themselves, right? Then once we have the Llama Guard will be used as an external component which observes the interaction logs between the user and also the large language model. It's actually an online process, right? And then it will decide whether the dialogue between the user and the large language model is actually safe or not. If it's not safe, then it will also tell us what kind of unsafe category the risk belongs to, right? So you can see that this is actually what what we can say. This is actually a discriminative task that is essentially based on a fast thinking process. So it sees the dialogue and gives just a label, right? Which is actually a fast thinking process that is different from what we are building, which I'm going to introduce shortly, right? Um, so while the importance of guardrail models have been recognized very well by the field, development of these models is still in a very early stage, and there are quite a few challenges I want to mention at this moment. The first is, again, we know that threats the guardrails need to handle nowadays are no longer as simple as those grammar attacks, right? These are more like, this kind of inputs, right? We are dealing with longer contexts, multiple turns of dialogues, and even with threads embedded in different modalities and even the UIs, right? And the second challenge is really regarding generalization. So we know that the complexity and the diversity of large language model tasks also lead to higher generalization requirements of associated guardrails. And the guardrails therefore are expected to handle highly diverse, largely unpreceded types of threats, right? Including harmful contents, model and system exploits, policy compliance risks, user authorization issues, and so on and so forth, right? All in just one system, right? And more importantly, the third challenge is actually the cost. So annotations of safety training data for guardrails are particularly expensive, and these are actually easily more expensive than a typical regular task for the large language model, right? According to some reports, obtaining high quality data may cost as much as a single annotator's hourly rate for just one high quality data point, and it will easily become more expensive. It involves multi-turn dialogues. Right. So against those challenges in the rest of talk, I will focus on this central research question of how to make guardrail models into stronger reasoners. Therefore, it will be more generalizable, right? And I will also briefly introduce the method that we have been trying to efficiently realize this goal. Right. So we introduced this concept of what we call a reasoning guardrail in this work titled ThinkGuard, which is published by this year's in this year's ACO conference. So ThinkGuard is a critique-augmented reasoning guardrail which seeks to make cautious and also transparent safety decisions. This is actually a work read by my second-year PhD student, Xiaofei, who is actually the guardrail expert who is also in this call. Right? So in comparison to traditional guardrails, a reasoning guardrail may not only just classify dialogue with large language models into safety or threat tasks. Importantly, before giving this kind of safety classification, it will conduct a careful deliberative thinking process to analyze the reason behind the dialogue, right? So it's to analyze the reason why the dialogue is safe or unsafe, right? This is like the thinking process you will see behind the scene if you are using those GPT models nowadays, right? So in short, reasoning guardrails are guardrails which not only classifies, but it also provides deliberative reasoning processes to enhance the precision, generalization, as well as interpretation of the guardrail. Right. So here's a intuitive example of using ThinkGuard. So suppose we ask the large language model to help us find a recipe of flavors which smell like almond, right? And suppose the large language model suggests, okay, so why don't you just mix benzaldehyde with amygdalin, right? Then a traditional guardrail will just conduct a fast thinking and give us a label, right, on top of this dialogue. So it won't be too surprising if it just tells us it's safe while ignoring what actually the consequences of applying these ingredients. But instead, ThinkGuard will deliberatively analyze the hidden risk behind the large language model response. So behind the scene, it will conduct a thinking process which will generate a critique that tell us that, okay, actually it's actually suggesting us using to use amygdalin, which will actually release cyanide that is actually poisonous, right? So therefore, the reason induces this reason will actually induce unsafety category due to toxicity, right? So obviously, adding this kind of reasoning process is particularly important to help the dialogue generalize to scenarios with implicit, complex, and even unprecedented risks, right? It also definitely gives us explanations so the large language model may choose to accordingly correct the response based on the rationale, right? So the next question is, we know that reasoning is definitely the to-go method to increase to enhance the generalization and the preciseness of guardrails. Then how do we really train a guardrail model to become a reasoner? The main bottleneck here is actually to efficiently obtain sufficient reasoning data to help the model to become a strong reasoning model because the reasoning data is actually very expensive, right? And the method we use to tackle this bottleneck is what we call mission-focused distillation. So to do so, we can take any safety training data that are used to train the traditional guardrail, right? Including any of those data that are used by Llama Guard, which where you will see that each of data point is actually a dialog that is labeled with a safety or unsafety category label, right? And we found that given any of this kind of data point, if you just let the large language model to explain, to actually decide whether the dialog is safe or not, it will not always be precise enough, right? Because detecting the safety risks are supposedly the weak spot of the large language model. However, if we give both the dialogue and also the safety decision, and we let the language model to explain why the safety decision is safe or not, just to connect the logical dots in the middle. This is actually rather straightforward for any of the existing reasoning models like those GPT models or DeepSeek models, right? Although we know that this kind of reasoning critiques in the middle is really the most expensive part for humans to write, right? So this is actually the strength of the existing proprietary reasoning models, right? So based on this rationale, we can efficiently obtain a large amount of uh, reasonably correct reasoning critiques for any of the safety training data off the shelf. And finally, distill them into a pre-trained guardrail model, such as the Llama Guard. This whole process will constitute a very low-cost way to transform a more traditional guardrail model into a reasoning guardrail, such that if we take the whole safety training data of Llama Guard and to generate the critique, it will just cost as much as let's say $60-$70 US dollars. Right. And in addition to directly reasoning critiques given the dialogue and also the safety labels, we also try to let the teaching model directly make safety decisions without seeing the safety labels. And although it will not always give the correct cases, but in a portion of the cases where it do give correct decisions, we consider them as something we call high confidence cases. And we do find that the reasoning critiques on those high confidence cases are often particularly high quality. So for which we will also mix them into the training process and prioritize them in training, right? So with this mission-focused distillation, as I said, that we can easily distill 10,000 level critiques using the GPT model by just costing around $60 of budget. Or we can also use freely available open source reasoning models like the DeepSeek or the Qwen models, right? And here's actually a quick head-to-head comparison between the Llama Guard 3 fine-tuned without reasoning critiques and also our ThinkGuard. And we do see that particularly in the cases where we have fewer training examples, we do see more advantage of the ThinkGuard. This actually shows that adding reasoning process is really an effective way to enhance the generalizability of the guardrail model. Right. So here are some full benchmark results, which shows that this is actually the results which are selected from more results that we have done in nearly all the available, uh, I would say, mainstream safety benchmarks in the community. And we do see that the by adding deliberative thinking process, it actually helps ThinkGuard outperform a wide range of models, including larger proprietary models like those GPT models, which has obviously done safety alignment, right? And also those 70 billion models, and also Llama 3. And and here we also, the benchmarks also covers various domains and types of threats. And I'll quickly just skip this and please refer to the paper itself for more discussions on more comprehensive results. But in short, really, ThinkGuard is actually globally generalizable and very precise in terms of handling threats of very different kinds in very different domains. All right. So mission-focused distillation is really the cost-effective way to create generalizable reasoning guardrails. Besides ThinkGuard, I also would like to mention a few contemporaneous works that also follow the very same principle, but these are the works which are very nice, but that are done almost at the same time, right? So besides ThinkGuard, I would also mention that there's the Guard Reasoner, which is published by a team from National University of Singapore. So this work is actually published by this year's iClear conference, right? And also later on, they extended this mission-focused distillation methods into vision language guardrail. This is a second work from that group called Guard Reasoner VL, right? And at the same time, we also see a similar work which extend the reasoning process into a multilingual setting. So this actually leads to something called a measurably. So in the meantime, we ourselves are also further extending the capabilities of reasoning guardrails. I would like to also briefly mention two of the most recent works that came out from our collaboration with Orbi. So one is the policy compliance guardrail, which we have just released online in the past few weeks. Right? So in this problem setting, in addition to safety issues in the cyberspace, we actually focus on justifying whether the AI agent's behavior complies with real-world policies. For example, if once again, right, if an online agent just go ahead and place orders, which includes champagne, right, the guardrail needs to identify that such agentic behavior is actually not policy compliant, right? It's actually violating the alcohol purchasing policy, right? So in this work, this is actually the work which is titled Towards Policy Compliant Agents. We have created one of the first benchmark that addresses this kind of real-world policy compliance issue of agents. And this benchmark contains over 60,000 annotated trajectory policy pairs that spans 5 different domains. And meanwhile, we also released a 4 billion policy guardrail model, which is very efficient and it's dedicated to handle this kind of policy compliance verification scenario. Right. So besides the policy compliance work, we recently have been also wrapping up a family of massively trained omnimodality guardrail. So this is actually a very comprehensive omnimodal reasoning guardrail that conducts safety assessments for inputs spans across text, images, audios, and also videos. Right. So all the modalities we can see nowadays. And we will release this guardrail very soon together with our collaborators and Orbi just in a few weeks. So please stay tuned. All right. So lastly, I would like to briefly mention 3 future research directions that I believe they could be very important for guardrail research at this point. The first is to enable lifelong learnability for those guardrails. We know that large language models are gaining new abilities and interacts with new environments in the system, right, in the long run. Then guardrails need to also persistently learn about new threats and risks, including new attacks, issues led by new policies, and even things happens in new types of environments it has not seen before. Right. So in as much as agents are getting augmented with persistent memory systems, we should also consider equipping guardrails with similar persistent memory mechanisms. This is actually one of the methods which is attempted preliminarily by one of our papers published also in this ACL conference. This year's ACL conference is titled Guardrail, a lifelong agent guardrail with effective and adaptive safety detection. So the second challenge I want to pitch is regarding inference efficiency, right? So while we are making guardrails more robust and incorporating reasoning abilities, and definitely we know that these stronger guardrails, which conduct deliberative thinking, would also lead to longer turnaround at inference, right? This is actually natural. So in this context, meaningful research questions would also include, can we find out effective ways of latent reasoning to accelerate guardrail inference, right? And also from the system perspective, we may also need to find out better ways to dispatch guardrail instances in a distributed large language model ecosystem, right? So the efficiency is also, I think, a pressing challenge at this moment for guardrails, right? Because guardrails they not only need to be precise and generalizable, they also need to be very fast. So it does not become the bottleneck or the system bottleneck of any foundation models, right? And finally, we know that large language models and AI agents are starting to assist us in critical in the food industry, healthcare, and scientific discipline in general, right? We very recently even seen quite a few federal grant supports in these directions, right? Such as the Fund SCI program from DARPA, which is actually something that I just accomplished, and also on the IALPA side is also the sci-fi program. Right. So in this context, we will soon face these risky scenarios. Suppose we have a scientific AI which starts to help us discover new recipes for perfume, or maybe also new food recipe, right? Then what if it suggests some recipe that again contains toxic compounds, or it lead to food that is not really safe to the user's health condition, right? What if this user is, for example, pregnant, so they should not really eat some specific food that is contained in a recipe, right? This is actually totally possible to happen, right? Then accordingly, while we are excited about new opportunities in AI for science, we should also at the same time consider knowledge-driven guardrails or personalized guardrails that safeguards AI's decisions in those critical domains. Right. Okay, so finally, I would like to thank my collaborators, especially Xiaofei, who has led the ThinkGuard work, but also my previous student in DeepMind and also collaborators from Orbi, which has recently been acquired into another company called Unifor. Yeah, and some references in this slides. All right, thanks.
Okay, thanks, Dr. Chen, for this fantastic talk. And let's open up the floor for Q&A. So for folks in the room, please feel free to use the raise the hand button, or you can also put your question in the chat. I'll be happy to read it for you.
Yes, I have a quick question. So, thanks for your good talk, yeah, Professor Chen. So, as you know, the embodied AI and robot learning some currently is a hot topic. So,
Yes.
when we deploy the guardrail models or the AI models in the robot learning, in physical robot learning, how can we ensure that safety? And this is first question. And last question, how do you think about the main challenges when we ensure the robot learning like in real world interaction?
Yeah, that's a very good question. I think for robot learning, there are even more challenges, right, in terms of guardrails or
Right, right.
safety assurance in general. Because at here, I guess we discussed this before in context of proposals. I think there's first of all the issue of data acquisition in different environments. So I would say from the large language model perspectives, you can always collect a real world interactions between human and the large language model. So that's why you see open data like wild chat, right? And also safety data annotated on top of those real world interactions from derived from those open dialogues. But I don't think this would easily obtained in the same amount for robot learning, right? So for robot learning, we need to do simulation to create scenarios and also trajectories. But at the same time, annotations for those simulated trajectories are going to be very expensive to human. But I'm not 100% sure, but I may suggest that methods like for example, methods like mission-focused distillation may be considered in this situation, right? Considering that annotations for robot trajectory is going to be very expensive, right? But at the same time, maybe if presented the scenarios, the trajectories, and also ground truth decision, large language models like GPT-5 or 5.1 may be able to give us efficiently give us a large amount of good quality reasoning process, just like what we do in the ThinkGuard work. The other way around is that I do think if you apply a guardrail in embodied agent, because you would expect even shorter turnaround than those large language models, right? Large
Right.
language models, they are actually conducting thinking by themselves. So it has some turnaround time. Then if you have a guardrail which also has some turnaround time, it won't cause maybe it won't cause a noticeable difference for the users of the large language model, but it will be totally different in embodied agents and even autonomous driving agents, right? So that's why I think the challenge presented in this slide may also be considered. Can we actually consider using some very fast implicit reasoning to improve the efficiency of the guardrail reasoning, at the same time increase reliability in comparison to just the pure fast thinking? Yeah.
Mm.
But I think this is an area which has a lot of challenges, a lot of issues to be discussed. Yeah. Thanks,
Yes,
Tony.
I think so. Yeah. So I think one of the bottleneck is the data costs, right? Yeah.
Yep.
Okay. So I saw like
So yes, that's great. We have a question in the room. Nidor Nuri, please go ahead.
Yeah, hi. At some point in the talk, you mentioned with the slower guardrails, as opposed to the traditional quotes traditional guardrails, that you mentioned interpretability.
Yes.
And is that intended only for the human, or is that also intended as feedback to the LLM?
That's a good question. In short, it can be regarded as a feedback to the large language model. Yeah, so we can always add this reflection step, right? So if the guardrail detects some unsafety category with the rationale, we can actually present this rationale to the large language model to let the large language model moderate and try to change the output, which is originally harmful, to become hopefully become not harmful, right? This is actually something that is very natural. Yeah.
Okay. And then can I ask a follow-on question?
Yes, please.
Sorry, it's not really a follow-on. It's a second question.
Yes.
Um, it's just something I thought of when the previous person asked you about robot learning. So in the case of domains like robots, it seems to me you
Mhm.
have a lot of domain-specific safety constraints. In other words, they're not sort of general knowledge. They're very, very specific to the domain the robot is operating in.
Yes.
Is that something then that you would have to train this guardrail model on as well?
Yeah. That's actually a very good question. So I think if we step back a little bit, I would say the first question is, do we really have to use a guardrail for, let's say, autonomous agents, embodied agents in specific scenario? So let's consider the difference between, let's say, autonomous driving agents and also large language models. I think a critical difference is that large language models or web agents, system agents in general, they are general domain models slash agents which need to tackle a lot of different scenarios, which is not specific to just a very specific kind of task scenario, right? So over there you will see the situation where for maybe let's say the thousands of tasks the large language model has learned, you would accordingly see thousand different kind of thousand different groups of threads, right? So that's why the motivation of using guardrails on top of a foundation model, a large language model, are as I said, right? So we will try to mitigate safety tax issues and also try to mitigate the need of frequent retraining, right? Because over there, the safety data can be out of distribution to a lot of the thousands of regular task train data. However, on the other hand, if we think about the embodied agent or autonomous driving agent, that is exactly a model, an agent, which is actually just focusing on one kind of scenario, right? One kind of task. So over there, the question is, should we really consider external guardrail, or what if the over here the safety data are most of the time out of the are actually in distribution to the task, right? I think that's totally possible, and I think at here choosing between the guardrail and also just injecting the safety slash more generalization data into the agent need to consider the trade-off of how much out of distribution, how much training data that's external to the regular tasks, to the model, to the agent itself, and versus whether there's a significant need of efficiency, right? So I do think that the large language model needs relatively less need in efficiency, but over there you will see much more cases where safety alignment data is actually external to the task training data versus in the scenario of embodied agent, it seems to be opposite, right? So you will need a much higher efficiency need, but at the same time, safety data could be naturally uh, in distribution. So all those safety data are actually annotated on the scenarios that the agent are likely to see in its daily performance, right? So in that context, I do think that maybe embodied agent represents really a very different area application area. So over here, we actually would consider more efficient ways of acquiring edge cases, but just to train them into the agent itself instead of using external guardrail. Versus on top of foundation models, we would actually consider using external guardrail. Yeah, I think that there's this kind of a key difference between these two areas.
Yeah, I agree. I agree. So in the case of autonomous driving and those kinds of models, um, you've got one difference also is that you've got well-defined safety constraints. In
Yes.
other words, you can almost state them formally, right? So
Yes.
is it would it be feasible to actually have something that incorporates those formal constraints and in other words, it's hard coded to enforce those constraints. Is that something that is reasonable that you've looked at?
Yeah. I think that would be reasonable, right? So that will be a formal verifier, which could be more efficient, but also at the same time, you would expect to update it less frequently than a regular guardrail. I,
Yes.
I, I do think, yeah, it's practical to add that on
Gotcha.
top of,
Thank you.
yeah. Yes, thank you.
Yeah, I love these discussions of safety for robot learning. So building on this, in robots, we often have a model because those are physical systems,
Yes.
and there are some techniques like control barrier functions that has been very effective in ensuring safety in certain aspects. On the other side, we have foundation models that is able to reason about the safety specifications,
Hmm.
especially those that are around the human and alignment. So we have these like two kind of different things, paradigms. So how do you like integrate them? Is it like, do you think there's be like some architectures that kind of leverage the benefits of both sides and decide when to use which, or like in general, like what's your thoughts on really kind of have a
Mm,
paradigm that have both the data efficiency but also being able
mm.
to be flexible.
Okay, yeah, that's a very good question. So, can we think about, let's say, so for those guardrail models, these are actually generally learned based on instance level annotations. These are learning not really from formally verifiable, not necessarily from, sometimes it can be formally verifiable, but not always formally verifiable policies, right? But in what I heard from you is that in robot learning, in a lot of situations, you would actually have policies which are formally verifiable, but regardless, can we consider turning any of these signals, regardless of whether they are verifiable or not, into just a unified reward model. So in that case, a unified reward model, or you may also consider this is a judge model. There could be a uniform architecture which captures both sides, right? Regardless of whether you directly learn from formal policy or you learn from like real instances, right?
Mhm. I
Yeah.
see. Makes sense. Yeah, another way is potentially leverage the coding capability of the foundation model to kind of build the model on the fly or revise the model, and then kind of run some simulation or kind of formal verification on the in
Yes.
the real
Yes.
time.
Yeah.
Yeah.
Yeah, I think that would be very helpful to tackle maybe the data acquisition bottleneck. Yeah,
Mhm.
yeah.
Okay. Interesting. All right. So let's see. Um, do we have any other questions from the audience? Yeah, actually, I have another question about the memory side of the agents.
Oh, yes,
So right now, many agents are equipped with memory, um,
yes.
just either to help people to have assist them better or being able
Mm-hmm.
to keep the workflows. So for the guardrails that you have presented, um, how do you kind of address the potential memory safety? Like, let's say the leakage of private information, or like in the interpretability framework, when you reason about the safety, um,
Ah,
would there be some uh, scenario where you reason with some sensitive information and that gets to be leaked to the user?
oh yeah, yeah. I get your point. Yeah. So I think we're talking about different kind of memories, but I'll also express some of my opinions regarding the memory leakage issue you described. So in this slides, right? So in this work, this is actually the cases where we augment the guardrail agent, the guardrail. We also can use the same kind of methodology to augment any agent, right? We have other papers, but I think this kind of memory augmented agents are actually pretty popular nowadays. Right, those are the situations where the agent is actually equipped with a long-term memory to learn from its experience, right? So over there, it would maybe do abstraction of the trajectories to make it more meaningful and combine useful lessons for similar kind of tasks and update the memory, insert in the memory. Maybe optionally it will expire if the memory has a limit, right? But I think the memory leakage issue would exist in the case where let's say there could be multiple agents operating on the same system, right? So originally they are just users. There could be multiple different users operating on the operating system, but different users may have different also different authority, but based on their user group, right? But that will be handled directly from the access control mechanism of the operating system. But now between the user and the operating system, there lies the agent. The agent is external to the operating system. But the agent itself has memory, right? It needs to memorize some information from the user, maybe the user credential. It will read write the system and get information from the system, but the accessibility is actually inherited from the user, right? So there will be indeed this kind of situation where maybe okay, let's say I have a user A, the user A is actually a super user, then there's an agent which represents a user A, so it can read any kind of information from the system, or also at the same time again from the user, right? This kind of information are critical information, but they will become something that is stored in the memory of the agent A. Then there comes another agent B, which represents user B, but user B it's just a normal user. But what if the agent B can interact with the agent A? So in that case, it will exploit the agent A and get whatever information user B cannot access from the beginning, right? Or maybe just get the credentials of user A. I think that's actually a critical issue, which I don't think that it is really tackled, right? So that means actually similarly, in the past, people have decided have been working on access control mechanism for the operating system. But now it seems like we need to think about the same for the agent layer that is between the user and the system. We need to also maybe design a very rigid access control mechanism that controls the interaction between agents, but ensures the same kind of privacy slash safety assurance like the operating system itself. Yeah. So in short, I think the memory leakage issue belongs to first. I think a different kind of memory, different kind of problems and the persistent memory of the agent itself. But I do think this is actually overlooked problem at this moment.
Mhm.
Yeah.
Yeah, interesting, interesting. Mm. Let's see, do we have more questions from the audience? Right. Since we've covered all the questions, we can wrap up a few minutes early and give everyone some time before their next meeting. So please join me in giving one more huge thank you to Dr. Chen for a fantastic talk.
Thanks everyone. Thanks me. Thanks Shangding. Hope to see you soon. Maybe I guess are you going to New York?
Yours
Yeah,
for
yeah,
sure.
sure. We will get to Europe.
Yeah. We'll see both of you there. Yeah.
Mm,
Right,
All
sure.
catch
right.
you,
Thank you.
everyone. Have a
Bye.
great weekend.
Bye.
Bye.